Okay, welcome back. Make sure that I am in frame. So, okay. Good morning, welcome back. What I want to look at today is continue with electrical machines, and this is electrical machines in respect of Terence Payne, electrical machines part 2, okay? I repeat, electrical machines part 2. Most peculiar, okay. So I'm just trying to make sure that I've got this in view, okay? Right, electrical machines part 2. And we're looking at stator construction, okay? Go in there and make sure that you can see that there fully, okay? As well itself. Right. Field winding, squirrel cage rotor, rotor shaft, steel frame or yoke, okay? On this figure 6.05 stator construction. As shown in figure 6.05, the stator stationary component comprises the field windings, which are many turns of very fine copper wire, wound onto formers. These are then fixed to the inside of the stator steel frame, sometimes called the yoke. Okay. The formers have two roles. One, to contain the conductors of the winding. Two, to concentrate the magnetic lines of flux to improve the flux linkage. The formers are made of laminated silicon steel sections to reduce eddy currents, thereby reducing the I2R losses and reducing heat. The I2R losses is in regard to power, watts, and that tells you whether or not the amount of heat you are producing, which becomes dangerous to the motor. So therefore, you need to keep this I2R losses to a minimum. The number of poles fitted will determine the speed of the motor. The rotor construction and principle of operation. Essentially, there are two main types of rotor. Squirrel cage rotor, wound rotor. Now, be aware, due to modern technology and etc., and the drives are going to space, we have produced probably different motors of alternative types. So do not just limit yourself to this. Do some research for yourself. Do a bit of experiential work is what I would call it. Okay. Squirrel cage rotor. In the squirrel cage, see figure 6.06, the bars of the rotor are shorted out at each end by end rings to form the shape of a cage. This shape creates numerous circuits within it for the induced EMF and resultant current to flow and thus produce the required magnetic field. And all I'm saying here is thin bars shorted out at each end by a thin copper end ring. Okay, and this is figure 6.06 squirrel cage rotor. Okay. I'll just bring you around a bit because I might have you a bit skewed. Okay. Figure 6.07 shows the cage fitted to the shaft of the motor. The rotor bars are encased within many hundreds of very thin laminated insulated segments of silicon steel and are skewed to increase the rotor resistance. So these are laminations all compressed together. Okay, that gives you your rotor. Tin copper rotor bars encased in thin 0.5mm laminated steel segments to reduce losses and skewed to assist starting. These are your bearings, okay? Now let's just have a look at what's on my left hand side here, okay? See what it says. And it says here, did you know squirrel cage induction motors are sometimes referred to as the workhorse of the industry, as they are inexpensive and reliable and suited to most applications, okay? Okay, let's see what we got. On the shaft will be two low friction bearings which enable the rotor to spin freely. The bearings and the rotor will be held in place within the yoke of the stator by two end caps, which are normally secured in place by long nuts and bolts that pass completely through the stator. When a three-phase supply is connected to the field windings, the lines of magnetic flux produced in the stator, rotating at 50 revolutions per second, cut through the bars of the rotor, inducing an EMF into the bars. Faraday's law states that when a conductor cuts or is cut by a magnetic field, then an EMF is induced in that conductor, the magnitude of which is proportional to the rate at which the conductor cuts or is cut by the magnetic flux. Make sure that as you have a good view of this, okay? Make sure you can come back from it, okay? Now the EMF produces circulatory currents within the rotor bars, which in turn results in the production of a magnetic field around the bars. This leads to the distortion of the magnetic field as shown in figure 6.08. The interaction of these two magnetic fields results in a force being applied to the rotor bars and the rotor begins to rotate or to turn. This turning force is known as a torque, the direction of which is always as Fleming's left-hand rule indicates. Now remember to look at Fleming's left-hand rule and Fleming's right-hand rule, okay, in regards to motors and generators. Wound rotor. Now in the wound rotor type of motor, the rotor conductors form a three-phase windings, which is starred internally. Starred, connected as in star. Internally, the other three ends of the windings are brought out through slip rings mounted on the shaft. Thus it is possible through brush connections to introduce resistance into the rotor circuit, although this is normally done on starting only to increase the starting torque. This type of motor is commonly referred to as a slip ring motor. Okay? Figure 6.09 shows a completed wound rotor motor assembly. Although it looks like a squirrel cage motor, the difference is that the rotor bars are exchanged for heavy conductors that run through the laminate steel rotor, the ends then being brought out through the shaft to the slip rings on the end. Okay? Now, the wound rotor motor is particularly effective in applications where using a squirrel cage motor may result in a starting current that is too high for the capacity of the power system. The wound rotor motor is also appropriate for high inertia loads having a long acceleration time. This is because you can control the speed, torque, and resulting heating of the wound rotor motor. This control can be automatic or manual. It is also effective with high slip loads as well as adjustable speed installations that do not require precise speed control or regulations. Typical applications include conveyor belts, hoists, and elevators. These are quite large motors and they actually have they're quite effective in the industrial environment. You will find these in car factories, places like which once used to be Dunlops and Fishers and Ludlows and so forth. You can tell how old I am now, you know. Okay, but those motors, but even Jaguar Land Rovers will now have these still in place. Okay. Now, figure 6.10 single-phase induction motor. Okay. The wound rotor motor is particularly effective in applications where using a squirrel cage motor may result in a starting current that is too high for the capacity. Oh, it's okay, I've just read that, haven't I? It's okay, I'm just missing my little point. Okay, so let's go to single phase induction motors. Single phase induction motors, okay, and that's our single phase induction motor, okay. If we were to construct an induction motor as shown in figure 6.10, we would find that on connecting a supply to it, it would not run. However, if we were then to spin the shaft with our fingers, we would find that the motor would continue to run. Why is this? When an AC supply is connected to the motor, the resulting current flow and therefore the magnetic field produced in the field windings changes polarity, backwards and forwards, 100 times per second. However, if we spin the rotor, we create the effect of the rotor bars cutting through the lines of force. Hence, the process starts and the motor runs up to speed. If we stop the motor and then connect the supply again, the motor will still not run. If this time we spin the rotor in the opposite direction, the motor will run up to speed in the new direction. So how can we get the rotor to turn on its own? If we think back to the three-phase motor we discussed previously, we did not have this problem because the connection of a three-phase supply to the stator automatically produced a rotating magnetic field. This is what is missing from the motor in figure 610. We have no rotating field. So because we have no rotating field, we need to create a rotating field within the motor itself, and we need to do that by, well, I would say phase shift, basically by making it think that there is a rotating field existent which causes the motor to rotate, thinking that it's following a magnetic flux. But let's see what we have. Here we are. Start winding high resistance, smaller cross-sectional area conductors compared with the run winding. Run winding, low resistance copper conductors, okay? Now let me bring this in here because we're going to need to look at that in a different way, and I'll make it smaller so we can get it all onto the same page. Figure 611, split phase motor induction, okay? Well, let's look back at what we were talking about. So what we're looking at now, the split phase motor induction start, induction run. We can overcome this problem, and we're looking at this problem here, okay, of getting it to start to rotate on its own, okay. We can overcome this problem if we add another set of poles. Position 90 degrees degrees around the stator from our original wiring as shown in figure 611. Sorry, excuse me. Now, When the supply is connected, both sets of windings are energized, both windings having resistive and reactive components to them. This is the resistance that every conductor has, and also inductive reactance because the conductors form a coil. These are known as the start and run windings. So here, what we've done now to overcome the problem, we're putting in a start winding into this, okay? We're putting in a start winding into this motor here, okay? All right, so that's what we're looking at. These are known as the start and run windings. The start winding is wound with fewer turns of small wire than the main winding, so it has a higher resistance. This extra resistance creates a small phase shift that results in the current in the start winding lagging the current in the run winding by approximately 30 degrees. So all we are doing here, we've created a phase shift in order to get the motor to self-start and to start running. And once we can create that shift, that motor will run every time you start it up. Doesn't matter whether it's day and night, sunshine, rain, whatever, it will start without hesitation. Okay? Let's just go back to show you what we're on about now in more detail if I can. Yes, I think I can. Okay. And I might simplify it, I think. And here's your waveform. Okay. That's your waveform showing you which is which. Now let me just go across so we can see what it is saying. You can see here strong magnetic field in the run winding, weaker field in the start winding. Okay. Strong magnetic field in the start winding, 30 degrees later, weaker field in the run winding. Okay. You can see by that phase shift alone, it has created a situation where the motor begins to think it is alternating, thereby it will run. Okay. Figure 6.12, run and start winding phases. Thus the magnetic flux in each of the windings is growing and collapsing at different periods in time. So that, for example, as the run winding has a strong north-south on the face of its poles, pieces, the start winding will only have a weak magnetic field. In the next instance, the run winding's magnetic field has started to fade, but the start winding's magnetic field is now strong, presenting through the rotor an apparent shift in the lines of magnetic flux. In the next half of the supply cycle, the polarity is reversed and the process repeated. So there now appears to be a rotating magnetic field. The lines of force cutting through the rotor bars induce an EMF into them, and the resulting current flow now produces a magnetic field around the rotor bars. The interaction between the magnetic fields of the rotor and stator is established and the motor begins to turn. And once it starts, it doesn't stop until you turn off the power. But you can then restart it at your leisure because it will then, the effect is there already. It is consistent. It is because the start and run winding carry currents that are out of phase with each other that this type of motor is called split phase motor. Okay? Okay. Okay. Once the motor is rotating at about 75% of its full load speed, the start winding is disconnected by the use of a device called a centrifugal switch. Well, I'll have to get my teeth or better teeth, which is attached to the shaft. Okay. And this is your centrifugal switch, which causes to throw open once disconnecting the start windings. Okay. Centrifugal switch, start winding high resistance smaller cross-sectional area conductors compared with the run windings. Okay. Run winding low resistance copper conductors. Okay. And this is figure 6.13. Split phase induction motor with centrifugal switch. This switch worked by centrifugal action in that sets of contacts are held closed by a spring. And when the motor reaches a certain speed, the spring operates the switch and swings and throws the switch open once the motor has reached that speed, thereby disconnecting the start windings spring. And this completes the circuit to the start winding. When the motor starts to turn, a little weight gets progressively thrown away from the shaft, forcing the contacts to open and thus disconnecting the start winding. It is a bit like the fairground ride known as the rotor, in which you are eventually held against the sides of the ride by the increasing speed of the spinning wheel. Once the machine has disconnected the start winding, the machine continues to operate from the run winding. Okay. The split phase motor's simple design makes it typically less expensive than other single phase motors. However, it also limits performance. Starting torque is low, at about 150–175% of the rated load. Also, the motor develops high starting current of about 6 to 9 times the full load current. A lengthy starting time can cause the start winding to overheat and fail, and therefore this type of motor should not be used when a high starting torque is needed. Consequently, it is used on light load applications such as small hand tools, small grinders, fans, where there are frequent stop-starts. The full load is applied after the motor has reached its operating speed. Reversal of direction. If you think back to the start of this section, we talked about starting the motor by spinning the shaft. We also said that we were able to spin it in either direction and the motor would run in that direction. It therefore seems logical that in order to change the direction of the motor, all we have to concern ourselves with is the start winding. We therefore need only to reverse the connections to the start winding to change its polarity, although you may choose to reverse the polarity of the run winding instead. I would choose to change the polarity of the run winding instead. The important thing to remember is that if you change the polarity through both the run and start winding, the motor will continue to revolve in the same direction. And that is something for you to remember. You can only change one or the other. Okay? Okay, I hope you found that useful. And let me just go back now and make sure that I got it all in view. And this is part 2 electrical machines. Let me just make sure get this into place. Alright, sorry, I'm just thinking let me change this, drop this down. Okay. Thank you. Okay, thank you. Have a good day. Bye-bye.